So here we will talk about carbon-13 NMR, which is actually quite simpler compared to proton NMR, and which builds upon the fundamentals of proton NMR spectroscopy as well. So before you watch this video, make sure you understand how proton NMR spectroscopy chemical shifts are to be understood, and then come to this so that it's going to be easier for you to understand. So just like we have hydrogens with higher electron density appearing at a lower ppm value, and electrons with hydrogens with lower electron density appearing more towards the left side of the spectrum, carbon also is going to have the same sort of what I would say the distribution or approach. Okay, carbons that are electron rich are going to appear at higher ppm value, which is what we call the high field region in an NMR spectrum. And as you go to carbons that are more electron deficient, you will start going towards the left hand side of the spectrum, which is higher ppm value or low field region in the spectrum. One thing that you will notice is in carbon-13 the scale is much bigger. Excuse me. It's going to go from somewhere from 0 ppm to 250 ppm. Okay, so that's that. Now, as we saw for proton NMR spectrum, right, for example, if we have primary hydrogens, they appear at a lower ppm value. You go to secondary hydrogen, hydrogen connected to a secondary carbon, they will appear slightly at a higher ppm value. And if you have a hydrogen connected to a tertiary carbon, that is going to appear at an even higher ppm value because of the same reasons I mentioned. Similarly, when you look at a primary carbon, it is going to have a peak somewhere from 0 to 20 ppm, primary carbon. Secondary carbon, because it is connected to two carbons, right, it is going to have a ppm value that is slightly higher, which is from 10 to 30 or 35 ppm. Tertiary is going to be, as you can see here, tertiary carbon is going to be from 20 to 60 ppm, and quaternary carbons is going to be 30 to 50 ppm, which I think I would say, like, it's approximately the same, let's say, right? So primary, secondary and tertiary, there is a clear difference, whereas when you go to the fourth kind, which is the tertiary carbon, you are going to see it approximately in the same range as the secondary carbon. Excuse me. And one thing that you want to notice is in proton NMR spectrum, you won't see a signal for anything that is attached to a tertiary carbon because there is no hydrogen connected to that carbon, whereas in carbon-13 NMR spectrum you will be seeing a signal for a carbon that does not have any hydrogen at all, because you're looking directly at the carbon and not a hydrogen that is connected to it. So that's that. So for example, if you look at say a molecule such as neopentane, this is a pentane, right? In proton NMR spectrum, you will see only one hydrogen. You will see a single peak. Whereas in carbon-13, you are actually going to see two peaks. One peak for the carbon that is on the terminal side, and also one carbon that is on the interior side. That is the that is what you will see in carbon spectrum. Okay, I'm not talking about multiplicities and all that in the proton NMR or carbon NMR. In proton there are multiplicities. You need to know how the multiplicity or splitting works, whereas in carbon you won't see splitting, because we deconvolute it so that we, as in the machine is made in a way that you only see a single signal without any splitting. Okay, so that it is simpler, because it gets very complicated if you look at splitting of carbons from the next by carbon and next by proton. So you will see only single peaks in carbon-13 spectrum. Anyway, this is the first part, which is understanding alkyl carbons. Now when you look at the next set of carbons, which appears anywhere from 40 to 80 ppm, that is going to be carbon attached to an oxygen. So the carbon that is attached to an oxygen appears from 40 to 80 ppm, because oxygen is electronegative. It takes electrons from carbon, making it more electron deficient, so it appears in that span. Now if you look at chlorine, which has a similar electronegativity as oxygen, again the ppm values for carbon attached to a chlorine is also going to be very similar to what you see for oxygen. If you go to carbon bromine bond, as you see, bromine is, as you know, bromine is less electronegative than chlorine. It is also going to have a ppm value that is slightly higher, because this carbon is not as electron deficient as this carbon is. And again, if you go to iodine carbon bond, the carbon is going to appear from 20 to 40 ppm. That's that. And if you look at a carbon nitrogen, a carbon connected to a nitrogen, it is going to be very similar to what you have for oxygen carbon, except it is going to be at a lower ppm value because nitrogen is less electron deficient, less electronegative, making this carbon slightly more electron rich than that carbon over there. That's basically what is based on inductive effect. And here, as we saw for an alkene in proton NMR spectroscopy, that this alkene can appear somewhere from 4.5 to 6 ppm, right? And it's significantly higher ppm value compared to what you see for alkanes. Similarly, here also in carbon-13 spectroscopy also, alkene carbons, because of the internal current, is going to have a higher ppm value where they appear in the spectrum. So it can appear, the carbons that is in part of an alkene bond is going to be somewhere from 100 to 150 ppm. Similarly, as we saw in proton NMR spectroscopy, aromatic rings, benzene rings, they are going to have hydrogens that appear around 7 ppm, right, which is higher than what you see for alkene hydrogens. Similarly, in C13 spectroscopy, aromatic carbons are going to have a slightly higher ppm value than pure alkenes. It is not as big as the difference you see here for a proton NMR spectroscopy for the hydrogens between a vinylic hydrogen and a benzylic hydrogen. So you are also, sorry, vinylic hydrogen versus a phenyl hydrogen, right? Here the difference is not as big. Okay, so this is a phenyl hydrogen, by the way, keep that in mind. A benzylic is that. Okay, that is a benzylic hydrogen, and as you know, benzylic hydrogens would appear around 2.1 ppm or 2 to 2.5 ppm. That's the range I would talk about. Okay, so that's that. And we can ignore imines and nitriles or cyanides. We don't have to worry too much about all the functional groups. But the more important part is what I'm going to talk about now, because in C13 NMR spectroscopy, there is a concept that is very frequently tested. So that's what we're going to look at right now. So if you look at ketones, okay, and aldehydes, right? So these carbons, they are going to be very highly electron deficient, mainly because the electrons are taken away by the oxygen to give a resonance form that has a lot of positive charge character. Okay, so because this carbon is very highly electron deficient, it has a ppm value of 220 ppm. So it anywhere about 200 is what you will see. So 200 to 220 ppm is where you will see the carbon that is part of the C double bond O in a ketone or an aldehyde. So both these carbons are going to be about 200 most of the time. Okay, that's what happens. Now when you take the same C double bond O that is part of a carboxylic acid or an ester, okay, or an amide, right, or it could be a dialkylamide as well. So in all these cases, these carbons, okay, even though they are attached to more electronegative element here, so this is an oxygen, that's an oxygen, that is a nitrogen, which is more electronegative than the carbon or the hydrogen you see here, right? Even though these carbons are attached to more electronegative elements like these carbons appear at a lower ppm value than 200. Okay, so pure ketones and aldehydes, the carbons are going to be about 200 ppm. Okay, whereas when you look at C11Os, the carbonyls, that is in carboxylic acid, ester, or an amide, they are going to be somewhere from 180 to 190 ppm. So here they say it's 170 or even 160 to 190, right? So it is not going to be above 200 ppm, and definitely it's going to be below 200 ppm or 190 ppm. Okay, that's what I would say, 160 to 180. And the reason for that is because these lone pairs are used for conjugation. The carbon here is not going to be as electron deficient as the carbon here is, making their ppm values appear to be lower in the C13 spectrum. So that's one of the most important distinctions you can make. So if you have a C13 NMR spectrum and you see that there is a signal at say 190 ppm, you can be fairly certain that you're looking at an ester or a carboxylic acid. Okay, if it appears like at say 165 170 ppm, that's a very good chance that it is actually an amide. Okay, it's an amide. So that's that. Whereas if you see something that appears at 210 ppm, that means you either have a pure C double bond O that is part of a ketone or an aldehyde. Okay, ketone or an aldehyde. So that is what you should remember for C13 spectroscopy.